The research paper introduces an approach to Hod Pair Capturing, HPC, a significant open problem in descriptive intermodel theory. It presents two principles, direct limit independence and bounded direct limits, which together imply HPC. The authors discuss the importance of descriptive intermodel theory in linking various set theoretic frameworks, focusing on the core model induction as a robust tool. They also introduce the conjecture 0.2, which deals with the existence of models with specific properties under the assumption of NLE and the presence of wooden and strong cardinals. The conjecture's importance lies in its relation to the proper forcing axiom and the existence of inner models with subcompact cardinals. The paper concludes by highlighting the Hod problem and its connection to HPC, emphasizing the need to solve HPC to advance in this field. Here is a combined summary of pages 3 and 4 of the research paper. The authors discuss the relevance of the Hod pair conjecture, HPC, to the study of set theoretic complexity and its connection to the core model theory. The classical approach to transferring set theoretic complexity from one framework to another involves the core model K and its parent model Kc. However, mild large cardinals, such as wooden cardinals, imply that the core model does not exist, and hence, it cannot have covering properties. The authors introduce the concept of a generic generator, which is a key concept in this paper. A generic generator is a Hod pair, P, sigma, that generates a transitive model M of AD plus NLE plus V equals L, R, such that R subset equal M. The comparison theory for generic generators is harder to develop and will be done elsewhere. The author's goal is to present a general approach to proving HPC using generic generators. They define the concept of a Hod pair generated model and introduce the notion of a generic generator. The key difference between generators and generic generators is that generic generators are not countable. The authors discuss the connection between generic generators and the iterability conjecture for Kc-Misch, which cannot be proven in ZFC. They also acknowledge the idea of proving HPC and other statements by calculating the power set operation inside Hod pair constructions, which is due to Steele. The authors introduce the concept of increment VGEN, HP, the set of all Hod pair generated sets of reals, and increment VGEN, Pe, the set of all a subset equal R that are generated by a pure extender pair. They state the main basic theorem about increment VGEN, HP, which assumes AD plus and shows that if increment gen, HP does not equal R, then theta reg is the theory AD plus. Theta is a regular cardinal. The paper discusses the concept of generic generators, which are crucial for understanding the relationship between the derived model of a background universe and the reals in that universe. A generic generator is a pair, P, sigma, such that P is an omega sequence of iterates of a background universe. Sigma acts on L, P, and it is an omega strategy. The main theorem of the paper states that if M is not generated, then there exists a generic generator for M. To prove this theorem, the authors use a sequence of iterates, M alpha, Pa, beta, alpha less than omega, of a minimal sound mouse M with a wooden cardinal that is a limit of wooden cardinals. They show that P, lambda, is a generic generator for M, where P is the direct limit of the sequence and lambda is the direct limit of the corresponding sequence of strategies. The paper also discusses the production of generic generators using fully backgrounded constructions of sufficiently strong backgrounds. It assumes that the minimal active mouse with a wooden cardinal that is a limit of wooden cardinals exists and denotes it as M. The authors then define a Suslin, Kosuslin capturing background universe V and set delta equals delta VGEN. They assume ADR and not HPC, which implies that there are good point classes beyond delta. The authors outline the main strategy for establishing HPC and other statements like it, which involves showing that the Hod pair construction of M reaches a Hod pair beyond delta. However, previous works, 14 and 18, assume stronger assumptions than NLE, such as no Hod mouse with an inaccessible limit of woodens and no transitive inner model of LSA. The paper aims to establish HPC and other statements using weaker assumptions. Here is a combined summary of pages 7 and 8 of the research paper. The authors explore the concept of generic generators in the context of inner model theory. They define a fully backgrounded construction, as a KC construction where extenders used are total extenders, and the background universe has a distinguished extender sequence. The authors then present lemma 3.1, which states that if delta is an inaccessible cardinal and M is a model appearing on some fully backgrounded construction of V delta, then there is no total extender E on the sequence of M with critical point kappa and resurrection F having a critical point greater than kappa. This lemma leads to corollary 3.2, which shows that if V is a premouse or an LBR premouse, delta is an inaccessible cardinal, and M is a model appearing on some fully backgrounded construction of V delta, then V delta satisfies, kappa is a strong cardinal. If M satisfies, kappa is a strong cardinal. The authors also present theorem 3.4, which is a restatement of theorem 4.1.12 from 18. This theorem assumes a D+ and states that if gamma is a good point class, gamma asterisk operator is a good point class such that gamma subset equal delta tilde operator gamma asterisk operator, and n psi is gamma asterisk operator would n which Suslin, Kosuslin captures some a element of lub gamma. Then there is a function f defined on R such that for a Turing cone of x, f x equals n asterisk operator x mix delta x sigma x satisfies certain conditions. The main theorem of this section, theorem 3.5, is then presented. It states that if V satisfies ADR plus NLE plus not LEC, then there is a pagan-Eric generator for delta gen, pay in V, G, where G subset equal call, omega 1, R, is V generic. Similarly, if V satisfies ADR plus NLE plus not HPC, then there is an HP generic generator for delta gen, HP in V, G. The proof of this theorem involves constructing an omega 1 sequence of iterates of M, where M is a psi mouse over X, and using corollary 3.2 to show that the strong cardinals of M are preserved in the iterates. The paper discusses the construction of a generic generator, focusing on the development of a class-size psi mouse with a Wood-in cardinal. It begins by explaining how to build M alpha plus 1 given M alpha, involving extenders and trees based on n asterisk operator y beta, delta y beta. The construction consists of models P xi and R xi, starting with P0 as M alpha, kappa plus alpha, M alpha. The process involves adding backgrounded extenders from W xi, and branches from W xi, with a limit step defining P xi as the limbs up of P zeta for zeta less than xi. The construction is shown to last delta y many steps, with a lemma demonstrating this. The analysis involves examining the failure of the inductive hypothesis IH xi, which leads to a contradiction. This ensures that the construction is well defined and can be iterated. The paper concludes by discussing the WTO P xi tree, defining U lambda as the WTO P xi lambda plus P xi tree according to lambda, and shows how P xi lambda plus P xi is a model in the construction. In the context of set theory, particularly in the realm of inner model theory, the concept of generic generators and their relationship with Wood-in cardinals is explored. A generic generator is a pair P sigma, where P is a transitive model of ZFC power set and sigma is a strategy for P, which is an omega 2 strategy. The main result of the paper is theorem 3.5, which states that under certain conditions, there exists a pagan-Eric generator, P sigma, such that sup W P union sulfur monophosphide less than omega 1 and all strong cardinals of P are limits of Wood-in cardinals. To prove this theorem, the authors use a fully backgrounded peg-producing iteration of a given mouse pair, n asterisk operator x0, delta x0, sigma x0. This construction involves defining a sequence of mice, M alpha, Ka, J alpha, beta. Alpha is less than or equal to omega 1, and a sequence of strategies, Sa. Alpha is less than or equal to omega 1, for these mice. The construction ensures that the final mouse M omega 1 has the desired properties. Corollary 3.12 further refines the result by assuming V semantically entails ADR plus V equals L, R, plus not LEC plus NWLW, where null stands for there is no omega 1 plus 1 iterable active mouse M such that M semantically entails. There is a Wood-in cardinal that is a limit of Wood-in cardinals. In this case, the authors show that for any V generic G subset equal call, omega 1, R, there is a pagan Eric generator, P, sigma, element of V, G, for delta V gen, P such that sup, W, P, union sulfur monophosphide, less than omega 1 and all strong cardinals of P are limits of Wood-in cardinals. The paper also discusses the concept of amenable linear iterations and introduces a definition for amenability in the context of premise. An extender E is said to be amenable to a model M if for any x in M and a element of LH, E, less than omega, A intersection X element of M. This property is crucial for ensuring that certain iteration trees on M have the desired properties. In addition, the authors mention the possibility of using Hod pair constructions instead of L opening square bracket E constructions to produce a HP generic generator. However, they note a gap in the literature regarding whether delta x0 is a Wood-in cardinal in the Hod pair construction of n asterisk operator x0 as developed in 28, definition 3.1.1. This issue can be resolved by quoting published results from 28 and 12, Chapter 3, Chapter 4, Claim 4.1, which show that the mouse construction of n asterisk operator x0 is universal in the sense that if n is the output of this construction, then sulfur mononitride, the stack over n, has covering in the sense that n asterisk operator x0 semantically entails Cf. Sulfur mononitride intersection ord is greater than or equal to delta x0. The results of 1 then imply that sulfur mononitride can be translated into an MS mouse. Call it M letting n be the L opening square bracket E construction of n asterisk operator x0 done as in 9. It follows that n is also an MS mouse and, moreover, S in semantically entails delta x0 is a Wood-in cardinal, and n asterisk operator x0 semantically entails Cf. S in intersection ord is greater than or equal to delta x0. Comparing M and N both being universal, we get that they embed into the same mouse queue, with iteration embeddings I, M right pointing arrow Q and I, M right pointing arrow Q. Since both are universal, we have I delta x0 equals I delta x0 equals delta x0. It then follows that M semantically entails delta x0 is a Wood-in cardinal, and hence L n semantically entails delta x0 is a Wood-in cardinal. The paper discusses the properties of generic generators, particularly focusing on the relationship between models and extenders. It starts by defining the concept of amenable linear iterations and their connection to iteration trees. The main branch of an iteration tree is used to construct models and extenders, ensuring critical points are below the image of an inaccessible cardinal. This setup is crucial for proving corollary 4.3, which states that if two premise models share the same largest cardinal and have the same properties regarding ZFC and the cardinal's inaccessibility, they are equal. The corollary is established by showing that one model is contained within the other and then using the equality of their last models. The paper also touches on the direct limit independence hypothesis, which involves the independence of certain models from specific parameter sets. This is done by defining the direct limit of a set of models and extenders and then stating the hypothesis in terms of generic generators and their properties. In this section, we demonstrate how the direct limit independence hypothesis, DLIH, can be used to compute the power set operation in generic generators. We show that if there is a non-generated set of reals, the L opening square bracket E construction of an n asterisk operator X model reaches a Wood-in cardinal that is a limit of Wood-in cardinals. This result also carries over to Hod pair generic generators, assuming one can resolve the issue raised in remark 3.13. We define a weak cut point of P and provide a definition of P, eta plus P from P, eta, where eta is a weak cut point of P. The computation shows that P, eta plus P is simple and yields a contradiction when we also assume that P, sigma, is backgrounded. The theorem assumes V semantically entails ADR plus NLE plus V equals L, R, and proves that under certain conditions, P, eta plus P is contained in ODVP, eta, X. The proof involves several lemmas and definitions, including the notion of a pagan-Eric generator and the concept of a weak cut point. The result is significant in the context of generic generators and the study of Wood cardinals. The research paper discusses the properties of generic generators and their relation to Wood cardinals. It begins by concluding that P0 equals Q0 based on the generator's properties and their extenders. This leads to the notion of a Wood cardinal as a limit of Wood cardinals. The paper then defines a bounded bottom part for a set increment and shows that assuming DLIH and boundedness of Wood cardinals, there exists a mouse with a Wood cardinal that is a limit of Wood cardinals. The proof involves a peg-producing iteration and the use of a strategy sigma to induce a self-justifying system. The paper also discusses the computation of power sets and the existence of superstrong extenders. It concludes by introducing the concept of bounded direct limits and shows how they can be used to prove LEC assuming NLE. Throughout, the paper emphasizes the importance of Wood cardinals and their properties in understanding the structure of the universe. Here is a combined summary of pages 19 and 20. Theorem 6.3 assumes that V models ADR plus NLE plus V equals L, R, plus not LEC, and for every A subset equal R, there exists an ALF background. It is shown that either V models not DLI, increment, or V models not BDL, increment. The proof involves a contradiction, assuming that V models both DLI, increment, and BDL, increment. A set of subset equal R is chosen such that gamma less than theta L, A, R, increment subset equals sigma 21, A, tilde operator L, A, R, and A is Waj above all sets in increment. In V, G, the union H of all M infinity, P, sigma, where P, sigma, is a pagan-Eric generator for increment is considered. It is shown that H element of V and H element of L, A, R. The concept of almost a full and a full sigma subset equal R is introduced, and it is proven that the set of almost a full sigma contains a club in V, G. Given in a full sigma, embeddings J sigma, R sigma right pointing arrow L theta L, A, R, and J plus R plus sigma right pointing arrow L, A, R, are defined. A set B of reals coding the set sigma element of omega 1, R, sigma is a full and X0 element of A, and a set C of reals coding the set sigma, tau, element of B2. Sigma subset equal tau and there is X element of tau intersection B that codes sigma, are introduced. A good point class gamma is chosen such that A, B, C, X0, R, element of increment tilde operator gamma, and a universal gamma set D subset equal omega times R is defined. The goal is to show that if kappa is a strong cardinal of K, then kappa intersection K is essentially contained in C gamma P kappa, implying that K has a superstrong extender. Claim 6.4 proves that if kappa is an inaccessible cardinal of VP delta, then for any P generic H subset equal call omega less than kappa, sigma H is a full. Claim 6.5 shows that MH sigma, where M is the direct limit of a set G of iterates of K. Finally, claim 6.6 proves that sup I, nu, less than I, nu, where I, P, H, right pointing arrow ULT, P, U, H, is the iteration embedding according to pi U, lambda upwards harpoon barb rightwards P, equals phi upwards harpoon barb rightwards ULT, P, U. The summary concludes by defining nu intersection M plus in R tau from K sigma, tau upwards harpoon barb rightwards M and J sigma, tau, M, showing that nu intersection M plus is ordinal definable from a intersection tau, x0, and sigma. Here is a combined summary of pages 21 and 22 of the research paper. The authors establish the ordinal definability of the set nu intersection M plus from a intersection sigma, x0, and sigma, leveraging the fact that C is in increment tilde gamma and x1 is chosen such that nu intersection M plus element of C gamma, sigma. This result is crucial in the proof of Theorem 6.3, which can be extended to Hod pairs assuming not HPC. The authors then shift their focus to justifying the plausibility of DLI and BDL. They introduce the concepts of PEBAD and HPBAD, which relate to the L opening square bracket E, construction of N asterisk operator X and the point class gamma asterisk operator. Conjecture 7.3 posits that if F is projective, then it is neither PEBAD nor HPBAD, assuming AD+. The authors provide evidence for this conjecture by showing that HPC implies conjecture 7.3 for many projective F. Conjecture 7.4 is then presented, which states that for every set B subset equal R, there exists F such that F is not PEBAD in B element of increment tilde base, F. The authors prove that assuming NWLW, they can establish a comparison theorem for generic generators, which implies DLI, increment, and BDL, increment. However, they note that to prove conjecture 7.4, they need to establish a comparison theorem for generic generators without assuming NWLW. The authors conclude by remarking that to prove LEC or HPC, it is sufficient to establish conjecture 7.3 and conjecture 7.5, which deals with the existence of a common iterate of two generic generators. Finally, they provide a list of references that support their research. Generic generators 23. The paper discusses the concept of generic generators, a crucial element in the study of inner model theory. It begins by referencing Steele's work on derived models associated with mice, which is a fundamental concept in the field of computational prospects of infinity. Steele's research provides an in-depth analysis of these models, outlining their structure and properties. The paper then delves into the derived model theorem, a key result in Logic Colloquium 2006. This theorem establishes a connection between the generic extension of a given model and its derived model, shedding light on the relationship between these two important concepts in set theory. Steele's outline of inner model theory is also referenced, providing a comprehensive overview of the subject. This work offers insights into the structure and properties of inner models, which are essential for understanding the hierarchy of sets in ZFC, Zermelo-Frankel choice, axiomatic set theory. Furthermore, the paper touches upon mouse pairs and Suslin cardinals, a topic explored in Steele's 2022 publication. Mouse pairs are a critical component in the study of inner models, as they help to establish connections between different levels of the set theoretic universe. Suslin cardinals, on the other hand, are a class of large cardinals that play a significant role in determining the consistency of various set theoretic statements. Finally, the paper references Steele's comparison process for mouse pairs, a recent work that aims to compare and contrast different mouse pairs. This research is vital for advancing our understanding of the relationships between various inner models and their implications for set theory. In conclusion, the paper provides a detailed exploration of generic generators, derived models, and inner model theory, highlighting the importance of these concepts in the study of set theory and large cardinals. The work referenced by Steele offers valuable insights into the structure and properties of these models, contributing significantly to the ongoing research in this field.